Well, today we're going to start talking about the open computing language known as OpenCL. OpenCL is sort of like CUDA. It's meant to solve the same kind of problem, is how do you do computing on a GPU without having to fake it by making it look like a graphics program. But it is different. And so we're going to talk about that and show some examples. I'm going to break this section up into four parts just to make the videos shorter to listen to. So, OpenCL. OpenCL, well, it's a product of the Kronos Group, which means it's an industry standard. It's a multi-vendor standard. It consists of two parts, the C++ part, and a C-ish GPU programming language. The relationship to CUDA is this very much looks like CUDA, except it's broken into two pieces. So if you think of a CUDA program and you extract the CUDA part and put it in a separate file, that's really what this is. Because this is an industry standard, the OpenCL programming languages, well, it runs on NVIDIA GPUs, AMD GPUs, Intel CPUs, Intel GPUs, mobile devices, and FPGAs, although I've never actually seen anyone do that, but I keep hearing about it. And like CUDA, it's at its best when you're doing very large amounts of data parallelism. You break your computational program up into lots and lots of threads, and thousands of these threads run on the GPU. OpenCL can share data and interoperate with OpenGL, and I'll show you how to do that. Also, there's a JavaScript implementation of OpenGL called, or OpenCL called WebCL, and well, same thing with OpenGL and WebGL, which means WebCL can share data and interoperate with WebGL. So yeah, we're going to have some fun with this, but it's largely the same philosophy that you've already seen in CUDA. Okay, who's in the Kronos group? Like, wow, lots and lots of people. This is the most recent chart I've had. This updates like every week is companies join, companies leave. But if you play Where's Waldo with this whole thing and look right here, whoa, who's in the Kronos group? Well, Oregon State. Yeah, about 10 years ago, I joined the Kronos group in Oregon State's name. It becomes so much easier to track these standards when you can be in on the email chatter and things like that. But yes, proud moment, Oregon State is indeed in the Kronos group. The really active OpenCL companies are here. You notice that, well, it's the usual hardware people, ARM, AMD, Intel, IBM, NVIDIA, Qualcomm, but there's a lot you probably haven't heard. Plus, there's software companies too. People like Adobe. So this really is sort of across the industry standard. And that's one of the reasons sometimes people choose OpenCL instead of CUDA is because it will run on any platform really, whereas CUDA is NVIDIA only. I was involved in a project a couple years ago where we were using a Qualcomm system on a chip, and this has full Linux and full OpenCL on it, so it was great. The project we were doing, I could program it in OpenCL. My biggest fear, if you look at the size of the quarter there next to it, my biggest fear is I would accidentally misplace it. It was so small. Okay, you've seen this before in the CUDA notes, but I just want to repeat it. Okay, so you have a C++ program plus OpenCL. It already is divided into these two pieces, and so you compile the OpenCL with anything you want. G++, the Intel compiler, Visual Studio, and then you compile the OpenCL code at runtime. It gets compiled in the driver for OpenCL. So you don't have to come up with a separate OpenCL compiler like you do in, say, in NVCC. Okay, The paradigm, once you've got the binary, is you run the CPU code, it whips across and runs GPU code, maybe brings some data back. You run some more C code, you send some things over here, and so on. Basically, you whip back and forth, and like we saw in CUDA, you're using the GPU as a coprocessor. Like CUDA, OpenCL wants you to break the problem up into pieces. If this is what you were doing in C, C++, you've got a for loop. Here's how you would rewrite that in OpenCL, and you notice a startling similarity to CUDA. The big difference is how you compute the GID. There is a built-in global variable that already tells you what the GID is, but the use of the GID, the global identifier, is exactly the same. The OpenCL language supports vector parallelism. Basically, this is SIMD, and your SIMD can be 2-way, 4-way, 8-way, or 16-way. Now, that doesn't necessarily mean hardware supports it. The language supports it, and if the hardware doesn't support it, it just does it as scalar. And in fact, that's what NVIDIA does. NVIDIA doesn't have SIMD hardware, but the language supports it. And so if nothing else, I like using it because I think it makes the code clearer. And I'll show you an example of that later on in this note set. Okay, just like before, the devices are made up of compute units. These are like blocks in CUDA. Each block, each compute unit has processing elements. This is the OpenCL terminology. And basically, each one of these runs a thread at a time. Work groups are arranged in these grids. Yep. So this is sort of the software view of the hardware situation. Yes, we're going to continue to beat the yellow robot metaphor to death. Is the grippers are these software work items. The robot itself is the software work group. Same memory model, and this makes sense. CUDA and OpenCL run on the same graphics card. You don't have to swap out graphics cards if you want to go from CUDA to OpenCL. And so, yes, it's the same hardware. So it's the same hardware diagram. Work items have private memory. Multiple work items within a work group can share memory. There is global memory. This is the multi-gigabyte memory out on the graphics card. Yep, they all have access to that. Same rules as before. So this is the setup really of what is OpenCL. And as you can see, it's CUDA with some changes in how you get at it. So that's it for the setup. We'll end that, but come on back for the next part because we'll get into specifically what makes OpenCL OpenCL.